Good afternoon, students. Let's go to this section of STEM alignment. What I will do for you today is to show the operation of the machine in STM mode. Okay. I will not be too worried about showing all the details of the operation and so on. I will just acquire the images in this remote operation and try to see some parameters of alignment and so on that can change the characteristics of the images. Okay, I have here some small amount of slides about it. Well, this is our machine, the FAG machine. And Professor Zagonel showed about inverted configuration for the STEM machine. This is for the dedicated STM machines. We have a STM machine. What we do is just to change the configuration of the lenses to have a different kind of focusing this the electron beam. Okay. In conventional TM, what we have is a parallel beam arriving to the surface of your sample. In STEM, what we have is a focused convergent beam that strikes your sample. Okay, it's the same system. It's just the configuration. It's all computer modulated. It's just the configuration of the lenses that are changed to have this kind of concentration of the electron beam. Okay. Well, when we deal with the STM operation, one very important characteristic of your system that we need to check is the appearance of the honkigram. Okay, the honkigram have this appearance. Okay, we will see it in the remote operation, and the honkigram. It's called a honkigram, but we can call it also the central zero-hour disk of convergent beam electron diffraction pattern. Why we can talk about this? Because what we see here is that we are striking the sample with a convergent beam, okay? And with this interaction of this focused beam with the sample, we will have the diffraction of the electron beam, and the zero order, the central spot of the diffraction, if you expand it, you see this guy here appearing, the honkigram. Okay. Well, why we have why we have this appearance for the honkigram? You can see here. I have another slide in front. Let me show. You can see some different regions of the honkigram. Okay. In the center of the honkigram, what we have is the infinite magnification of your material. Okay. And when you go from the center of the honkigram to the border, what we see is the deformation of the image in a radial way at the first moment, and azimuthal deformations to the border of your this object, the honkigram. Okay, these deformations in the image are all related with aberrations of the lenses of the microscope. Okay. Thinking about it, you can think that it will be a good practice to try to be rid of all of these aberrations when you acquire an image, okay? How to do it in an experimental way? We can put an aperture here, okay, to limit the amount of the amount of the electrons that are arriving to your probe, okay. Then limiting the amount of aberrations that you can put in your probe, okay. This is what we try to do. Well, you may had some lectures about these aberrations now, okay? Here we have a ray diagram for an ideal lens, okay? You can see that all the rays are focused in the same point in the optical axis. This is not the true for real lenses, okay? All the electrons that arrive at the borders of your lens will be focused first, early than the expected point for focusing. Okay, this is caused, I guess you know now, by what? Non-symmetric magnetic field through the diameter of your lens. Okay, the center of your lens will have the most homogeneous magnetic field, but at the near edge of your lenses will have a very high magnetic field, and then these cause this kind of distortions and the aberrations that we see in the honkigram. Okay. Let's see what I have here. Well, what do we get when you have the honkigram? Okay. We are in a diffraction mode of the microscope. We are simply illuminating this sample with the beam, the focused beam, okay? And then what we have is a shadow image of your sample, okay? When you illuminate with the beam, simply you have the shadow, something like the old projectors of for lectures and so on. Okay? When you go through the focus, here is the sample. Okay, here's the sample. We are here illuminating in an over focus mode. Okay, then the rays, the electron rays, they are focused before the sample. Okay, because it is over focused, then the magnetic field is higher than the ideal, okay? And then when you have the overfocus, you have this projection image. When you are in the correct focus, the Gaussian focus, what you have is the appearance of the honkigram. And then when you go to under focus position, where the crossover of the beam is occurs after your sample, you have the same image, the same shadow image, but now it will appear inverted. Okay? We'll see all of these experimentally. Well, here again, we have our honkigram. Okay? And we have also, sorry, need some water. We have here now some of the procedures that we need to do to align the Stm mode in the best way, in the excellent way. The first thing that we get is the astigmatism of your probe. Okay, you need to have ideally a very circular probe, okay, with a finite diameter that will strike your sample. If it is astigmatic, we will have some distortion. Here you can see that it looks like an American football ball, okay? That means that it's distorted in this direction, okay? It is an evidence that we have astigmatism in this image here, in this honkigram here, okay? And then, well, talking about the improvements that we have with new machines, the corrected machines, what we get, you saw here, how it looks like a conventional honkigram in a machine, in an uncorrected machine. When you go to a corrected machine, what we get is a very larger area inside the honkigram where you do not have any non-distortion, okay? All of these, let me get this one, all of these parts, first this radial distortion, and then the azimuthal distortion, you may be able to see that there are more than one circle around the honkigram. All of these are related with first order, second order, third order aberrations of your lenses. And then people are working in the development of the correctors, okay? And what they get nowadays is something like this. It's not that visible here, but here you can see that here's this C5 aberration corrector, okay? You have a very large area without any distortion, okay? You can see here the uncorrected limit is in the center. The second generation of correctors, there you expand the area with flat, with homogeneous illumination inside the honkigram by this amount. And then here, the third order, and here is the expected optimal resolution, the limits that, the theoretical limits that we can get, okay? You can think about why to expand this area of the honkigram without any distortion. If you think that we are looking for the in diffraction mode, what we are seeing here is the zero order diffraction spot, and it is related. It is the scale here is in milliradians, okay? It is related with space, okay? In the reciprocal space, okay? And then if you have the possibility to have it expanded, for sure you have here you can resolve you can have resolution that is related with this space here in the reciprocal space, okay? If you expand here in the reciprocal space, in the real space, you have smaller characteristics being resolved, okay? And then if you get the possibility to have it really large, okay, in the reciprocal space, it means that you have a very, very sharp probe that is able to resolve smaller distance in the real space. It's clear? Yes? Okay. Well, for the STM, we will scan the probe. Okay, I guess Professor Zagonel told you about this mode of operation. Okay, we will generate a probe, that it's very much useful for spectroscopic experiments, okay? Well, we have this requirement that the beam it must to scan parallel to the optical axis in all the moments during the scanning, okay? This is done by these deflector scan coils. It deflects the beam this way, in a way that always you have a parallel beam striking your sample, okay? And the idea of this STM images that they are not magnified by lenses, they are magnified by the size of your scanning, okay? It is a matrix. The smaller the size you scan, the higher the magnification you get, okay? Well, here is some idea, again, about the way it scans your sample, okay, your specimen. Will always have the diffracted spots fixed related with the optical axis, okay? During the scan, as you are parallel to the optical axis, in all the moments that you scan, you always will have the direct spot always in the center, and the diffracted beams always fixed in fixed positions related with the optical axis, okay? Well, in this way, we can, if we put a detector exactly here, we will get a kind of a type of image. If you put a detector in this position, we will have another type of image, and so on. We can choose. This mode of operation is very flexible. We can choose the kind of information that we get, and we can do it with some. It's easy to do it in practice. Okay, we can choose it for different experiments. Okay. Well, and then what we get is, if you get the central here, the direct spot of the diffraction pattern, we will have bright field image. If we get the diffracted spots, we can get ADF, annular dark field images. If we get a detector that is positioned here, for example, you have the high angle annular dark field. And then you get the famous Z contrast images. Okay? Well, let's do it in practice. I will operate here the machine. Let me just turn it off. Well, I'll leave it open just to as a reference. Well, as we are doing, I will simply start the machine. Okay, I will open the beam valve, and I will ask here for viewing. Yes. The microscope is previously aligned in conventional Stm mode, and then I will just change the configuration for Stm mode. As I said, it is computer controlled. It's very easy to do it. It's just to push the button and it will be in another configuration. For sure, you need to align it again. I left the machine previously aligned. I guess we will not have problem with it. but it's not that complicated. Okay. Well, this sample, it's a tungsten carbide with palladium. Okay. You have here my preferred sample is catalysts. Here you can see the border of the grid, okay, and some particles distributed on on this carbon film. This is the lacy carbon film with the ultra thin carbon. Well, let's go for. I will just acquire an image. Let me see a good. I'll try to find a good particle. So let's leave this particle here as a reference. You can see we have here a carbon support with these particles that are this tungsten carbide. And then tungsten is very, very heavy. We have a very large difference between the Z atomic number of the particles and the substrate, the support. This is very instructive for us to see. I will acquire here an image just as a reference for us. Okay. And now, I will go to, now I will go to the Stm mode. The Stm mode, we just need to press this guy here, mode changing. Oh, no. Now we are in a completely different situation. We have this center spot here working, and then now I am in a camera lens of AADF 5. It is used for HADAF experiments. Now I will go to a larger probe, okay? Larger camera lens, I'm sorry. I need to stop the beam. Let me just get it here. Well, here. This is the software that controls scanning in this machine. I will ask for, it is scanning, you see? I will ask scan spot. Now it is fixed. It's not moved anymore. I can come here and open the apertures, okay? We work without apertures, and now I have the projection image, okay? Here I am out of the particle. What we see now? We see now, exactly as I told you, the shadow image of the sample. You are illuminating, okay? Let me see here. Look. We are illuminating the sample and looking for the projection, okay? What we can see, if we change the focus, we will expand or decrease the size of the projection, and then let's do it. I will work here in the objective. In the objective focus. Let me just tem foco do objetivo aqui, não? Objetivo é o foco do objetivo. It's not familiar for me. Let's try it. You see it's moving. Now I'm going to a very over-focused situation, and then what we see is the shadow image of our sample. Now I start to have some aberrations entering the camera because I'm really far from the crossover position. Okay, and then we can see this projection image. It's something like you are illuminating your paper with some drawing and looking in a wall, you see something there. Okay, and then if we come back in the focus, what we will get following this diagram here, I was over focused. Now I am going to the Gaussian focus, and I will go to the other side, okay, of the crossover. And then at the exactly the moment where you have the Gaussian focus, you have the honkigram appearing, okay? You can see we can manage with the size of the honkigram just by focusing or under-focusing or over-focusing, okay? Then if we go inside the honkigram, what we will get is the inverted image. This way here. I am by the side of this, and it simply appears in the other side of the screen. Okay? And then this is something like it is shown here. You go from one side to the other side, you just have this inversion of your honkigram. I will just here. What? Yes. No. It's just projection image. Is mass density that it's controlling here, okay? Not Z contrast. What? Sorry. Yes. This is like it's a shadow image, a real shadow image. You are illuminating, and what is in front of your path of the beam will be dark, and what is thinner will be brighter. The spherical shape? Yes. They are related with the distortions, with the aberrations of the lenses. I will do it, I will do the honkigram a little bit smaller to try to discuss this. Have a look here. Well, here is, you see the honkigram. Now you see that it's really misaligned. We have a lot of astigmatism here. I will try to correct it first, continuing. What I need to do is to control here. See, now I am changing the stigmator coils of the machine, of the condenser. I can move the shape, change the shape of the honkigram, making it more or less circular. The idea is that it is really circular. This is the correct alignment of the beam. Okay. Yeah. To have you to form a honkigram, you need to have something. Yes. This is a very thin carbon film. Okay, amorphous. But you need to have some material in front of the beam. If not, you will not have this deformation of this image. Okay? Yes, but they appear very strange. Let's see. Here you are on the material. You see? It's not that understandable. Well, coming back here, what we get, well, it's clear for you the idea of the inversion. You see, when we approach the material, it starts to appear in the other side. Okay? And also, we have here the projection, and in these radial distortions, you start to have what people call the infinite magnification of your material, okay? And when it goes here inside the azimuthal distortions, you have both here and here this infinite magnification of your sample. It's not that controllable, okay? Then this is why we do not use this mode for acquiring images. Because if it is infinite magnification, it's a good idea to have to have an image about it, but it's not easy to control it. Okay? But honkigram is very useful for the alignment of the Stm mode. Okay? Well, I guess what I want to show about the honkigram is this. You have some question about the honkigram and so on. You understood you got the idea of the projection, the inversion of the image, and so on. Well, what we have here, when you have this, I will make another, I will make it slower to have a better image. And I can get something like this. Oh no. Well, it's okay. Now I have a better image. And we are here, and we start to have the material. It's clear these radial distortions, you see, when I change the size of the honkigram, you can see clearly that from here, from the center to here, you have these radial distortions and then the azimuthal distortions. They are all defects of the lenses. What's the size, exactly size of the honkigram? Okay, because you are convergent, you are focusing the beam on your sample, okay, and then you have the best focus, the best possible focus on the material, okay, and then what we need to do for alignment is to try to find this best situation to position our condenser aperture, okay? It's another interesting thing that I guess Professor Zagonel told you about the objective apertures related with the illumination in STM. I don't know if you are thinking about it. This, when we are in STM mode in this machine, this is, I will move the condenser aperture, but for the STM mode, it works as an objective aperture, okay? Because I'm dealing now with the illumination of the probe that I'm forming, okay? It's not just condensing like in the case of conventional TM, okay? Well, now I will make the beam. When you see simply a very, very small whole annular hole, not a whole figure in your image without this image in the center, when you first, when this image in the center first disappear, then you have the best focusing, the best situation for the alignment of the aperture, okay? Then we get something like this. You continue to see the annular shape of the beam, okay? But you can't see the image inside the honkigram. And then what we need to do now is to insert the aperture. For this machine, for this machine, the third aperture has the size, the correct size to eliminate the most part of the aberrations, what it's possible to be eliminated. The best situation that we have for this machine is the third aperture. I will insert the first one just to show you. It's really not aligned. This is a very big aperture, but it's not aligned. Well, let's go for the second one. Try to see something. Nothing. And the third one, nothing also. Very good. I will open it again. I'm here. I will need to center the, well, Carlos will try, will try to put it in the correct position. Remote operation is really oh yes, thank you. Now we are with the second aperture. Here the first one to show you, it's very large, okay? And then the idea to try to cover some of the aberrations is you can't do it, okay? And then you go to the second one, you continue to see it's not the correct size, okay? And then the third one, it's a good size to try to be rid of the aberrations, okay? Then I need to position the aperture around the honkigram. You see, it's not, this way, you can be rid of some of the aberrations, but for sure, you are continue to include many of them in the system, because it's not, it's an uncorrected machine. You can't be completely rid of it in this operation, okay? Then I will make it a little bit smaller here to try to, well, it's a little bit distorted. You agree with me? It's not really symmetrical with the aperture. But it's okay. It's important to be symmetrical related with the center of the honkigram. You can deal with astigmatism during operation. In your image, you do the best looking for your specimen. It's another possibility. Well, now I will stop this viewing here. Okay. And I will call Vishnu. Vishnu.
Yes.
Please remove the top camera. Yes. Well, let's put it online to see if Vishnu is working well. Yes. Now we are without the top camera. I will stop this. What I will do now is to change the camera lens. Okay, that is here. I will. Yes. Okay. Thank you. I will change the camera lens for the position that it's suitable for AADF imaging. Okay. We'll have it now. I need to make some configurations here of brightness and contrast, and now it's okay. And now we can by using here the DigiScan system, we start to have our images by scanning now. Okay. In the left image here, we have the bright field image in the machine. Let me show you. In our machine, here is the screen, and the camera, the bright field camera, is positioned here. The HADAF camera is positioned here. Okay, they are in different positions. And then there is some misalignment between them, and I need now to make it aligned. Okay. We just put it this way. Okay. Here. Well, this is the system that we have. Okay. Now it's interesting to compare the material, the two viewings of the material that we may have. I guess this is the same part of the material. I'm not sure. I guess this guy here is this guy here. You agree? Yes or not? We can rotate it by 15 degrees. Rotate it by 7 degrees. Oh God. I will make it 0. But it's the same part. This here, you have this particle here, and this particle here that it's here also. I will go closer to show you. You see? This is what we get. This is the difference that we have in imaging both in both modes. Both are bright field, but with this in this mode here, we are including all the beams to form the image, the diffracted beams and so on. Here we have just the direct beam, okay? And we have also this image here that's very rich. I will make it better, just to minimize a little bit. It's very sensible here. The high angle contrast is very sensible with the height of your sample. If you have a two three-dimensional specimen, you have the correct contrast and brightness settings just in a very thin layer of your specimen. It's very important to have it very thin. In this case, I just crushed the material and spread it on the grid, and then I have some large blocks of the carbon. This is what we are looking now, okay? Well, with this, let me just make it a little bit closer. If you are investigating this material, you will see clearly here I have the possibility to ask for this is the search mode. I have the possibility to see the preview. That is, it's a little bit more. I have a little bit more resolution. It's not as fast as it's a little bit slower than the search. And I have the record position that I may get even better images. Okay. Now we can do some focusing, some fine focusing. Actually, I used to use this mode here to get the best focus. I go really close to some particle. Okay. Let me just well, if you move the focus, you can see focusing and defocusing for sure of your sample. Okay, we can see also if we are or not with residual astigmatism in the condenser. Okay, it looks to do not have something because it's not distortion. Okay. I make something like here for the best focus. And then we can look in the preview mode. It's a very strange sample. Looks like an ET. And then we can ask for the acquisition. And then it will scan very slowly with many pixels. I have here 124 by 124 with a slow scan mode. And then I get the best image I can. Looking for this image, we can see that this part here you can think, oh, it may be the metal part. And with this image here, as you have a direct dependence on the Z, the atomic number of the sample, by the brightness that you have, you can simply say, yes, it is a metal particle. Okay, for this is the highest Z in the image, for sure. Okay, all these very small spots here, you can also do the attribution that they are metallic particles, metallic nanoparticles that are completely distributed on the surface of this carbon support. And here it's very interesting that you have this shell here around the particle that have a smaller Z than the particle, and then you can think, knowing your system, you can make the correct attributions for this kind of distribution of contrast in the images. Okay. If we go a little bit farther, we can have a look like this to see the homogeneity of. You see, when I go to the two three-dimensional part of the material, I will have this kind of brightness distribution. This is when you have a path for the electrons, a large path of the electrons through the material, it will scatter and scatter, and then you may have some a lot of brightness that perhaps are not related exactly with the presence of particles, but they are related with a very long path inside the material. Then you have more probability of scattering and so on, and then you may have some distribution like this. To interpret correctly the Z contrast images, it's important to have a thin material. It's important to be sure that you have a thin region of your material for this. Okay, I will ask here for the acquisition. And it's interesting, we can see here, if I come and try to make the contrast here well distributed, I ask for a smaller contrast, then I start to have it not, I start to have dark regions in the image that actually were in places where actually I have material, but for related to the contrast here, I cannot see the image. Yeah, I start to make it flat. Okay. And well, here. Another thing that it's interesting is I will stop the beam here. I will turn off the AADF detector. Then now I just have this guy working. Okay, the other is not working anymore. And now I will play a little bit with the position of the beam. Okay, remember. Now what I have is something like I am here. What I have in bright field detector, I am illuminating with the central spot. Okay, direct beam. And then I have this nice image of your material. And now, if I change, if I come here, if I come here, these are after your sample. You have the projection lens that will control this camera lens, and then the angular distribution of these diffracted beams, okay? How it projects for the detector. If you ask for a small camera lens like the AADF, you will project its opening something like this, and you are in this situation. If you ask for a larger camera lens, we will continue this angle, but now it will strike the sample in this position that it's distant from the center, okay? And with a fixed camera lens, you can move the position of the diffraction pattern around the detectors, and change the contrast that you see. Now, I am in the bright field detector, okay? If I come here and play with the PLA, the projector lens, the position of the beam with the change in the projector lens, I will have something to show you. Let me just find everything here. You know which is the PLA here? Okay. Well, now I may have it. Let's see. Let me put it this side here. Well, now I may have the PLA and let me put it down. You see, I am in the bright field detector that is aligned with the optical axis, and I will change the position of this direct beam around this central, this bright field detector that's in the center of the projection. Then what do you expect to see first? What do you expect to see if I change this? If I move the diffraction pattern on the bright field detector that is in the center of the optical axis, you have a central spot and some spots around. Okay, you have some scattering of the beam and so on. What do you want to see? What do you expect to see? Think a little bit. If I change the position of the beam that is striking the bright field detector, in some moment I will change, and then the diffracted beams will start to strike the bright field detector. And then I would expect that with some movement, I will start to see the annular dark field contrast, the diffraction contrast in the bright field detector. Okay, let's try to play with the detector to see if we get it. Now I have anything, nothing. Wow. Well, here we see something like I told you. Here I have the bright field, the conventional bright field. Okay. The particles that are heavy appear dark. When I move the beam, the particles start to be bright, okay? But for sure, it is not the correct operation of the machine. Then we just can see that it changes, but we cannot acquire an image in this forced configuration, okay? Let's try another way to see. Here I have everything. See, here I have something interesting, okay? It depends on, it's completely out of the correct operation, and then there are some directions that it will work better than others. But here it appears completely different from the bright field position. It's clear for you that why you have this contrast, because you are moving the diffraction pattern through the detector. And I would expect something similar when operating the, I will try to put in the center again, something like this. And if now I get the high angle annular dark field detector, now I am with it now. If I can illuminate the detector that it's in high angle, if I can put the central disk there, I would expect to have also a bright field image. And then let's try to do it. There is some, it's very far from the center, and then it's not that easy. Yeah, I'm not sure if you can do it. I guess it's too far from the center. Yeah, actually it's too far from the center to get it. Well, anyway, this is what I was showing. Let's put both again to work. Yes. And now we can see the effect of changing these. I will put a little bit more magnification. Yes. Now we can see the effect of changing the position of the beam. You can see that the bright field detector is much more sensible to any change because it is in the center of the optical axis. Okay, and then you can see this. Make it brighter. You see that the changing in the position affects both detectors, but the bright field is most affected. Okay. Well, I guess this is what I have to show. You have some question? Would like to me to play something? I will try to do this. Yes. The difference between the setup of ADF and this change that I did. Yes, the difference is that for this specific machine, it is projected, it is arranged to have the ADF detector in the exact position that it is in the center of the optical axis, and by changing the beam like we did it, we are including many distortions in the beam and so on, and then you have actually in the bright field you see the ADF signal, but it's not well controlled. You just see qualitatively, you know, that, oh, okay, now I have all the diffraction, the high angle scattered electrons hitting the bright field detector. But it's an approximation. It's just to show actually not possible to acquire a good image with it. Okay? Because this machine is configured for exact position of the detector. I don't know if I answered your question. Yes? Okay.
More questions?
Questions?
So let's thanks
Okay.
Dr. Érico.